So, we have learned magnetism, a magnetic metal in the previous discussion, in which we have seen that how a spin only model in one dimension actually can be solved exactly and gives rise to a magnetic metal. If you include the spin-spin interaction in the z direction, a gap will open up and then we will have a magnetic insulator depending upon what is the magnitude of the gap. So, let us now look at more carefully magnetism, and we do it as an example of the ongoing discussion, but it also helps us to understand magnetism in particular, and we are going to talk about ferromagnetism to be more precise. So, let us talk about ferromagnetism, where by ferromagnetism what we mean is that the spins are all pointing in the same direction. So, when the spins all the spins are pointing in the same direction, we get a magnetization of the system. So, there is a bulk magnetization that exists, and this is put into use in various applications of magnets. So, the first thing that comes to our mind is that the magnetization versus temperature curve. So, magnetization versus temperature. And as I told that we are going to talk about ferromagnetism in particular. So, that looks like, so the magnetization is in the y axis and this the temperature is in the x axis. So, it is a transition which is like this for external magnetic field equal to 0, which we denote by H, and this point is called as Tc. So, when the bulk magnetization vanishes and the system loses its complete magnetization and it becomes a paramagnet, and the same plot in magnetic external magnetic field in presence of the external magnetic field looks like this. So, so this is of the order of typically Tc is of the order of for some materials which we will see such as nickel, it is of the order of, it could vary from something like a few Kelvin, maybe around 40 Kelvin to about maybe even 1000 Kelvin, and so 1000 Kelvin. Let me do it more carefully. And we will list out various values of Tc. So, what happens is that at Tc the magnetization vanishes and the ferromagnet converts into, or there is a transformation, phase transformation into a paramagnet, where which results in random alignment of spins. And we have shown two graphs, one is in the presence of external magnetic field, which is the outer curve, and the inner curve is with the magnetic field equal to 0. So, now what happens is at small values of field, the magnetization is proportional to the field. So, this is the external field, and we can write a proportionality relation with this, where chi is called as the susceptibility. And H, as we said, is the external magnetic field. So, this is valid for low fields. Of course, we have nonlinear phenomena which involves higher order of the external field, where the magnetization ceases to be linearly depending on the field at very large fields, but we will only stay within this domain where the magnetization is proportional to the field, and we can talk about a relation, linear relation between magnetization and the magnetic field to be having this kind of relation. So, now let us look at how the susceptibility, which is an important measure of magnetization, how that behaves with temperature. And so, susceptibility versus temperature. And we can have a 1 over chi plot versus T, which simply looks like a line like this, a straight line like this, which has a slope, or rather it can be represented by a formula which is like C divided by, where C is a constant, C divided by T minus theta, where T is the temperature and theta is some characteristic temperature, which we are going to list out in a while. And also very close to the transition, that is the ferromagnet to the paramagnet transition, we have the T actually, or rather the chi actually depends on the temperature in an interesting way, and which is often called as a universal behavior, and which can be understood that if you look at the log of chi, which is base 10, it is chi versus temperature, and then it looks like a straight line again, and this tells that the chi is actually 1 divided by T minus T c whole to the power gamma minus gamma. And so, this is a straight line. If we, I will simply erase this such that it looks like a straight line, and so it is a straight line like this, and where gamma is some coefficient, or rather some number, which is an indicator of the universality class of the transition. And so, at large temperature rather, so at large temperature, the susceptibility, which is chi, obeys a law called as Curie's law. And so, this can be written as what we have shown in the, so this is written as it's, so chi is equal to C divided by T minus theta. So, that tells us that 1 over chi goes as T minus theta divided by C, and also in the vicinity of T c, in the vicinity of the transition, which occurs at a temperature T equal to T c, the chi actually goes as T minus T c divided by T c whole to the power minus gamma, and this is will tell you, as I told, that it tells about the universality class of the transition. So, let us list out a few values for known ferromagnets. So, we have, so there are materials and there is a T c and this characteristic temperature theta. So, if we list out a few known materials of which show ferromagnetism, which is iron, which is about 1041, theta is 1093, nickel, which is another known ferromagnet, which is has a T c of 631 Kelvin. These are all in Kelvin, and this is a 650 Kelvin, and a gadolinium has a 293 T c 293 Kelvin, which is almost room temperature, and slightly higher value of theta, and a chromium Cr Br3 So, this has a Tc of which is very low, which is 37 Kelvin, and there is no datum available for CRVR3 for the value of theta. So, these are some ferromagnets, some known ferromagnets. So, before we go to the many body theory of understanding ferromagnets, let us see how we can understand it in a simpler language of ferromagnetism, and let us do models of ferromagnetism. And write down a simple model and try to solve it if possible. So, in presence of a magnetic field, let us call it as B. So, this magnetic field is often interchangeably used by H and by B. B is usually called as magnetic induction and H is called as a magnetic field, but however, sometimes that difference is not spelt out very explicitly, and one can write down Hamiltonian, which is a G mu B and a B dot S I and sum over I, and a minus J I J S I dot S J. So, the first term is that coupling between an external magnetic field B. So, this is the B is the magnetic field, external magnetic field, and S I are the spin vectors. All right. So, and of course, we have to define other things also. G is it's called as a Land G factor, and mu B is the Bohr or it's a magnetic moment, is a magnetic moment, and Jij is a nearest neighbor spin-spin coupling. So, this is a Hamiltonian, which there is a system of non-interact or the system of spins which are placed in an external magnetic field. The first term denotes how an individual spin couples to a magnetic field, and the second term is that there is an interaction between two spins which are at neighboring sites I and j. So, when I write this form, that is put I and j in angular brackets, they mean that I and j are nearest neighbors. So, there is a nearest neighbor spin-spin interaction. The amplitude or the magnitude of the spin-spin interaction or the coupling is given by Jij, which could be a constant for all I and j, or which may not be a constant for pairs of any pair of I and j. Now, this model is quite complicated to solve in 3 dimensions, and often there are no solutions, exact solutions, unless you are ready to make some approximations. And let us solve the scalar version of the model. So, this is what we are going to do, and scalar version of the model, and which is, we already know that it is called as the Ising model. Okay. And so, that Ising model looks like, so my spin vector has can only assume 2 orientations, which is up and down, that is called as the Ising model. So, my Hamiltonian now becomes G mu B and a B and S I Z sum over I, and a minus 2 j sum over I and j S I Z S j Z, I and J are still nearest neighbors, but now it is a scalar form of the spins that are considered, and we have discussed this before, that in order to avoid double counting, we have put this factor, and this is the Hamiltonian that we need to solve. And we define the magnetization as let us call it with Mi, which is equal to a Siz. Okay. Siz. Now, with this notation, my Hamiltonian becomes equal to this G mu B, B sum over I Mi and 2j Mi Mj. And this is written as G mu B, B divided by 2 sum over I alpha I minus j by 2 sum I equal to 1 to n alpha I plus 1, where alpha I equal to 2 Mi. So, basically these are the alpha i's will take values which are either plus 1 or minus 1, and if you notice that this sum, or rather the second term, contains a z n by, so z and n by 2 spins. So, these are the total number of spins that is there, and if we add a term which is alpha n plus 1, we have to understand that alpha n plus 1 is same as alpha 1. So, the n plus 1th spin is made as the same as the nth as the first spin. So, that we have an open chain and so on, and this open chain now has been put into a closed form, and so the last one and the first one is connected, and we have a closed system such that my alpha n plus 1 equal to alpha 1, and this is called as a periodic boundary condition, and this periodic boundary condition is enforced on the problem in order to solve it. So, it is periodic boundary condition, and this is the open chain. So, the open chain has been converted into a periodic or rather a closed chain by applying a periodic boundary condition. Now, how to solve this Hamiltonian? One way of solving is the Hamiltonian is to write down the partition function and see that if the partition function has any closed form available. So, the partition function is written as z equal to alpha I and exponential minus beta E n alpha I. Now, I will repeat for convenience that this is the canonical partition function, which means that it is a partition function for a system which is in contact with a heat bath at temperature T. And this is the form of the partition function where the energies, or which is we could have written H as well. So, we this is the same as what we mean by this is actually alpha I and exponential minus beta H alpha I, and as you saw it here that H is a function of alpha I. So, this H is a function of alpha I, and so you have to exponentiate it, multiply it with beta, and then take the negative sign here, and then sum over all alpha i's that are possible. But look at this simplicity of this formula, that alpha i's can only take values which are plus 1 and minus 1, because of the fact that s i's or the spins are only z component of the spins, and the z components take a value which is the z component of the spins take values which are +1 and -1. So, even if it looks like a complicated formula to solve, or rather summation to compute, it is not so. We will see that here, and we will use a technique which is called as the transfer matrix technique to solve this. So, in order to do understand ferromagnetism from very simple considerations, we have written down a general Hamiltonian where the spins are interacting with the neighboring spins, and they are in presence of a magnetic field, and there is a Zeeman coupling, as it is called, as a B dot S coupling at each site. B is uniform, magnetic field, the external magnetic field is uniform, and that problem has very complicated solution, and in 3 dimension it is not possible to solve unless you do some approximations. You can solve it numerically by doing exact diagonalization of a finite number of spins, but that is not the focus here. The focus is to actually solve this model by using analytic techniques. Then that Hamiltonian was converted to a 1-dimensional Hamiltonian, which is like an Ising model in presence of a magnetic field, and we are trying to solve the Ising model in presence of a magnetic field and in 1 dimension. And this requires us to compute the canonical partition function, which is written as this. So, this z can simply be written as alpha I equal to plus minus 1, and these are, there are n of those. So, this is alpha, so this is alpha 1, and there is alpha 2 equal to plus minus 1, and then there are sums of this kind, and alpha n equal to plus minus 1, and we can write down terms which are like k alpha 1 alpha 2, k alpha 2 alpha 3, and all the way up to k alpha n plus 1, but as I told that because of the periodic boundary condition, alpha n plus 1 is same as alpha 1. So, the advantage of this expression is that each of those k's, we will see what these k's are, each of these k's involve 2 spins at a time. So, this term involves the first and the second spin, where for alpha equal to 1, alpha 1 equal to plus 1 and minus 1, alpha 2 equal again can be plus 1 and minus 1. Similarly, for alpha 2 and alpha 3, and then alpha 3 and alpha 4, and continuing all the way for n spins, and this term is equal to alpha n alpha 1. So, so each of these k alpha 1 alpha 2, you should work it out carefully from this formula, that formula for the partition function that is written over here. So, this is equal to minus beta g mu b b. So, I should write here that beta equal to inverse of temperature, or it is 1 over k T, where k b as it is written here is called as a Boltzmann constant, which has a value which is often you would find it in any book. So, this divided by 2 and alpha 1 plus alpha 2 divided by 2 and plus beta j by 2 alpha 1 alpha 2, and this is the form of each one of those k expressions that are written inside the sum. So, and this can be summed over, each one of those k's can be summed over for values of alpha 1 and alpha 2, or alpha 2 and alpha 3, or alpha 3 and alpha 4, each having value plus 1 and minus 1. So, this requires us to solve a matrix problem, where this k actually looks like a matrix written like this, where this is for alpha 1 equal to 1, alpha 2 equal to 1, and this is alpha 1 equal to minus 1 and alpha 2 equal to minus 1. In this basis, one can write this as exponential minus x plus a. I will tell you what x and a are, and exponential minus a, and this is exponential minus a, and this is exponential x plus a. So, where my x is equal to g mu b b divided by 2 k T and a equal to j over 2 k T. So, what is shown here is the following, that each of those k's written in the alpha basis, which are, so there is one term for which alpha equal to 1 and alpha equal to alpha 1 equal to 1 and alpha 2 equal to 1. So, that is given by, so this should be more carefully written as, so we have a 1 1 and that is equal to, so this is the 1 1 element, and alpha 2 equal to minus 1 here. So, we have to write it as if we have these things. So, there are 4 combinations, alpha 1 equal to 1, alpha 2 equal to 1, alpha 1 equal to 1, alpha 2 equal to minus 1, alpha 1 equal to minus 1, alpha 2 equal to 1, and alpha the other term is alpha 1 equal to minus 1 and alpha 2 equal to minus 1. So, if you write it in that basis without writing it like this, then it looks like each of these k's will look like. So, one term is this, this term is the first term. So, this is the first term, and there is another term which is alpha 1 equal to 1 and alpha 2 equal to minus 1. So, which tells that this term cancels out because one of them is plus 1, the other is minus 1. However, this becomes exponential minus beta j by 2, which is written by a. I will show you that. So, these terms are cross terms when one of them is plus 1, the other is minus 1, and these one of them is, so this one is for alpha 1 equal to 1, alpha 2 equal to 1, this is alpha 1 equal to 1, alpha 2 equal to minus 1, this term is alpha 1 equal to minus 1, alpha 2 equal to 1, and this term is for alpha 1 equal to minus 1, alpha 2 equal to minus 1. So, these are the 4 terms. So, so this is written here. You should do it and convince yourself that you get a matrix of this kind for these 4 unique combinations, and this is the matrix that we have to solve. And so, x is equal to g mu b b by 2 k T and a equal to j over 2 k T, and so we have the full z, the total partition function can be written as the trace of k and n to the power n, because if you see, this is not only true for alpha 1, alpha 2, it is true for alpha 2, alpha 3, it is also true for alpha 3, alpha 4, it is true for alpha 5, alpha 6, and so on, and alpha n, alpha 1. So, we have similar k matrices coming, and so the entire thing, the entire partition function will be the product of all these matrices, and since we are doing a sum, it will convert into a trace. So, trace of those k's raised to the power n for n spins, and this is the form of the partition function. Now, you should understand that all the internal spins or all the internals alphas, that is, what are the internal alphas? Alpha 2, alpha 3, alpha 4, alpha 5 and alpha n minus 1, they are all summed over. They are all summed over, and we have the only alpha 1 and alpha 2, sorry, alpha 1 and alpha n are not summed over, or rather they remain, and that is what gives rise to this formula. So, it is a trace of that, and because it is a 2 by 2 matrix, so K has 2 eigenvalues. And those eigenvalues, let them be lambda 1 and lambda 2. So, my Z, since it is equal to trace of k to the power n, so this is same as lambda 1 to the power n plus lambda 2 to the power n. So, this is a general thing that you should keep in mind, because I am taking a trace and of n's 2 by 2 matrices. So, finally, this is going to be a 2 by 2 matrix, and those will have, each one will have 2 eigenvalues lambda 1 and lambda 2. So, the whole thing will come as lambda 1 to the power n plus lambda 2 to the power n, which can be simply written as lambda 1 to the power n and a 1 plus lambda 2 by lambda 1 to the power n. Now, you can see that if my lambda 1 is a bigger eigenvalue, this term goes to 0 for n going to be very large, because if this is the leading eigenvalue, lambda 1 is a leading eigenvalue, lambda 2 by lambda 1 goes smaller with each power of n, that is the spins, and when n goes to very large, I am left with only, so if my lambda 1 is greater than lambda 2 among the 2 eigenvalues, my z becomes only 1, and I need to solve only one of the eigenvalues of this matrix, which is shown here. So, and that the bigger one, and then I raise it to the power n. So, I can one can easily do that, and one gets a lambda 1 2, which is equal to e to the power a cosine of hyperbolic x and plus minus sine of hyperbolic square x plus exponential minus 4 a whole to the power half, and that is it. So, these are the lambda 1 and lambda 2, where lambda 1 corresponds to the plus sign and the lambda 2 corresponds to the minus sign, and we can simply take lambda 1, which is equal to exponential a and this term plus this term. That is what is going to be used in calculating the partition function. So, what do we do after calculating the partition function? We calculate the free energy, and the free energy is calculated using F equal to minus k T log of the partition function, which is simply equal to minus n k T log of Z1, sorry, log of lambda 1, not Z1. It is a, because we have decided to take the larger eigenvalue, it is a log of lambda 1, and the magnetization can be derived from the free energy, and which is equal to minus del F del B. Of course, in the limit b going to 0, that is what the definition says. So, we will have limit b going to 0 here, and this is equal to n g mu b by 2. You should do it and check, it is a very simple algebra, g mu b by 2 k T, and we have a sine hyperbolic square g mu b by 2 k T and plus exponential minus 2 j by k T whole to the power half. So, this has to be written with, so this whole to the power half, and let us put a, okay. So, that is the form for the magnetization, and interestingly it can be seen that m goes to 0 as b goes to 0. Okay. So, if there is no external field, a one dimensional such spin model does not show any magnetization. This is called as the spontaneous magnetization. So, there is no spontaneous magnetization of a 1D Ising model. If only we put the external magnetic field, then there will be magnetization there. And for B going to 0, so we have not still done the B going to 0 limit. So, which if we do that, my magnetization looks like G square and mu B square divided by 4 K and exponential j over k t by t and B. So, that is the form for the magnetization as a function of temperature, and also so this is that chi, which one can rather this is not the chi, because you have a temperature which is I mean. So, this is basically the chi, because the chi is nothing but del m del B, and this is equal to exponential j by k t divided by t. And apart from this factor, so this is equal to so 1 over chi that goes as t exponential minus j by t, which can be written as t 1 minus j by k t and plus. So, I have expanded the exponential and kept only the first order term, and this is equal to t minus j over k b. Now, you see that this is very similar to chi equal to c divided by t minus theta. So, our intention was to derive the Curie's law from a Hamiltonian, from a calculation, and this gives the derivation of the Curie's law, where the 1 over chi looks like T minus some characteristic temperature, which is J over K Boltzmann constant. And if you simplify this, then chi looks like, formally looks like as if it is some constant divided by T minus theta. Theta is some characteristic temperature, and which is here in this case it is J over K. So, this is the simple discussion of ferromagnetism in a model Hamiltonian, which arises out of spin-spin interaction. And once again, I had pointed out that this model has no spontaneous magnetization, which means that as you switch off the external field, the magnetization would vanish. At small field, the magnetization looks like this, as it is shown here, and the susceptibility looks like it has a form which is like this. We have dropped this the initial factor here, just kept only the T part and associated the energy, or rather the which depends on J over K has the characteristic temperature, which is theta, and then we have derived how chi depends on temperature, which is simply a 1 over T minus theta, where theta is some characteristic temperature. So, this is called as Curie's law. Now, let us see the same thing, or rather ferromagnetism from Hubbard model. So, and in particular we are going to derive what is called as the Stoner criterion. All right. So, what was the interaction term? So, we will write down the Hamiltonian, the Hubbard Hamiltonian once more, which is minus T C I sigma dagger C j sigma. There is a sum over I j, which are nearest neighbor, and there is a spin sigma, and there is a u n I up and n I down. There is a sum over I. So, this is called as the on-site interaction between the electronic spins, and since exclusion principle prohibits up spins to be present at the same side, but there could be up and down spins present, and which would have an interaction of this form, it is very clear that if u is switched off, that is which is called as the atomic limit, will have a metal given by only the kinetic energy term, and if u is much larger than T, we will have an insulating term, which means that the electrons will not be able to hop from one side to another, and the spectrum will be a large gap opening up due to u if u is much greater than T. Okay. So, this, as we said, that this has no exact solution in 3D, and we are even in 2D. We are going to make some approximations, and this approximation is called as a mean field approximation, or in this particular case it is called as a Hartree-Fock approximation. I will tell you what it is. So, in order to solve it, we will have to use this approximation, which is also called as the Hartree-Fock approximation. We will see this more elaborately when we talk about Green's function, which we are going to start very soon. Hartree-Fock approximation. And so, suppose you are sitting in a class, and you have friends who are sitting right beside you, and there are some friends who are sitting very far away from you, who cannot communicate in any way while the class is going on. But however, the people who are sitting in the right in the vicinity, that is in your just near neighborhood, they can actually speak to you, or they can point out, or they can communicate in some form with you. This is really a many body phenomena, because you have some interaction with people who are right at the vicinity, and you have lesser interaction with people who are far off, and even lesser interaction with the people who are farther off. However, if I make an approximation that you are sitting in the class, and the rest of your friends who all the other friends other than you can be considered as if you are in an external or an effective field, because of all the students present, all the friends present in the class. That is, I am not making any distinction between the friend who is right in your neighborhood and the friend who is very farther off. I am treating both of them to be equally, or giving equal importance to them, and saying that you are feeling an average field due to all your friends in the class. So, if you want to go beyond that, want to make a better approximation, then you would say that somebody who is in the neighborhood has more interaction with you than someone who is at the farther off positions, and there could be fluctuations, or there could be corrections to this average field picture or the mean field picture. So, we will go with the mean field model, where you are considered as if you are facing, or rather feeling, an effective field from all your friends. So, we would particularly concentrate on one spin in the system, and that spin, as if that spin is facing an effective field from all other spins in the system. So, to do that, what we need to do is that we can split this term. Let us write it. So, I will write this, and Ni up, Ni down, and U, Ni down, Ni up. So, you see here the down spins are facing an average field, which is U into the average up spin density. So, as soon as I take an average or an expectation of this between the, say, the state of the system or the ground state of the system, this becomes a number. So, this is the field that each of those spins, down spins, will be feeling, and similarly, without making any bias towards the up spins, the up spins will be facing this field. So, this is the average field or the mean field that each of those spins will be facing or feeling. Now, understand that my Ni up, one kind of spins is much greater than the other kind of spins because of the ferromagnetism. So, this is saying that one species outnumbers the others. And this is the essence of ferromagnetism. So, you know that in a ferromagnet we have predominantly or majority spins are pointing in one particular direction. So, in this model we do not have to have an external magnetic field to be present. And now let us simply define magnetization. We will not define bulk magnetization, rather we will define what is called as the sublattice magnetization, which is at a given site Mi, this is equal to Ni up minus Ni down. Okay. And so, the magnetization is same at all sites because of all the up spins are facing a potential which is u into the sum of all the down spin densities. So, how do we calculate this magnetization? So, this magnetization M is same as M, which is for all sides. So, M equal to epsilon epsilon F, let us call it epsilon delta to epsilon F, and there is a d E into n up minus this is an epsilon. Okay, let us write this as make it more clear and write this as epsilon A. I will tell you what epsilon A is, some energy, and to epsilon F and d E and n down E. So, we are simply computing the average upspin density, which is the density of states of the upspin, and integrated over energies from epsilon A to epsilon F. I will just tell you what epsilon A is, and minus the downspin density integrated over epsilon B to epsilon F. So, this model here has given rise to a band picture which looks like this. So, there is an upspin band. So, this is the downspin band and there is an upspin band like this, and my Fermi energy is here. So, this is my Fermi energy, and so this is the downspin, this is the upspin, and this is where my Fermi energy is, and my epsilon A is right here, or epsilon up if you want. So, that is the bottom of the band for upspin, and this is the bottom of the band for downspin. Now, you understand that if I have to know what is my total upspins or average number of upspins, then I have to take the density of states of upspins and integrate those from here, this point which is known as epsilon A to epsilon F. That is, I will have to integrate over all these place where the upspin is there, and in order to do it for the downspin, I will integrate from epsilon B to epsilon F, which is all these downspin. So, I will do. So, the magnetization will be the shaded area on the right minus the shaded area on the left. And so, what is my, so if I take a middle point here, so this is my delta, let us call this as delta, I will define what delta is, and this is my minus delta. So, this is also delta, but this is so this is for delta equal to 0, there is a reference line, this line is a reference line, and you have a delta. So, from that reference line all the way up to the Fermi energy, the gap is known as delta, and from there again the reference line to all the way to the epsilon A, which is the bottom of the upspin, it is called as delta. So, if you have this nomenclature, then my M can be written as minus delta to epsilon F, which is epsilon A to epsilon F. So, this is equal to minus delta, and n of, so d e, and we have a n e plus delta. So, the density of states is at energy E plus delta minus a delta to epsilon f. So, that is this point marked by, say, let us call is as P. So, the from P to epsilon f, so that is my the second one, which is a d E n E minus delta. So, this is my n up E as written earlier, and this is my n down E. You know that n up is much greater than n down, which is why the magnetization is large. And so, now since E is greater than delta, E is much greater than delta, because delta is the gap. So, we can do a Taylor expansion of the density of states, and each of those n E plus delta can be written as d n d E delta, and n E minus delta can be written as d n d E minus delta, and then I can write down skipping one step, which you should fill up, which is equal to 2 delta, where I have not defined delta. So, delta is equal to u m by 2. So, m equal to 2 delta, and I have delta to E f d n d E and a d E, and now this delta is much smaller than epsilon f. So, we are talking about epsilon f, which are of the order of a few electron volt, where delta is very small. So, epsilon f being much greater than delta, we can approximate delta to be equal to 0. So, we can take, or rather change this the lower limit of the integration to 0, and then this m becomes equal to 2 delta and the density of states computed at the Fermi, which is nothing but equal to m u n epsilon f. So, this will tell you, since magnetization is not equal to 0, we get a condition for ferromagnetism to occur, which is equal to 1 over u. So, this is called as the Stoner criterion. So, let us see what Stoner criterion is, and so this tells the ferromagnetism will occur in a system in which, if I have m versus the u, which is the electron-electron interaction. See the difference between this problem and the problem that we have done earlier, that is writing down a Hamiltonian, a spin only Hamiltonian, and solving it via computing the partition function, is that that model did not have any electrons, it was only a spin model. Now, we are having an electronic model. So, there are electrons which can hop from one place to another, which is a more realistic model, because the spins have to be carried by somebody. Spins are not, they do not exist on their own. So, the electrons carry the spin. So, a spin only, or rather an electronic model, is more reliable and more realistic than a spin only model. So, here a Hubbard model is an electronic model. So, this electronic model is, we are trying to find how ferromagnetism can be derived from the from this electronic model, and in the process we have found out a criterion called as the Stoner criterion, and which tells you that the density of states for the electrons at the Fermi level has to be inverse of this electron-electron interaction, which is a very surprising condition that we have found. And so ferromagnetism, for ferromagnetism to occur, we need a critical electronic coupling, a critical electron-electron coupling is required, which is you see some critical coupling. so that the NEF is equal to 1 over UC. So, it is inbuilt in the problem what is the density of states at the Fermi level. So, the electron's contribution to the density of states of the Fermi level is decided by the system itself. However, that has to match with a critical electron-electron coupling for ferromagnetism to occur. So, that gives you a more realistic picture about ferromagnetism, and what happens is that this is like this. So, you have a U equal to UC here. So, below that there is a paramagnet, and above that this is a ferromagnet, and we have this as the, so this is the Stoner criterion. So, in order for ferromagnet to happen, your N epsilon F has to be greater than 1, and this is a very stringent condition, that is the electron-electron interaction multiplied by the density of states at the Fermi level will have to exceed unity, that is the value has to be more than 1 in order to have ferromagnetism, and it is quite a stringent criterion, and iron, nickel and cobalt satisfy well this criteria. So, this is called Stoner criterion. So, to summarize the discussion that we had just now is that we wanted to understand magnetism, and in particular ferromagnetism. We have written down a spin only model and have solved it in one dimension and with Ising kind of interactions, and we found that it gives a ferromagnetism where it yields which is same as the Curie's law, and it gives you a characteristic temperature for the ferromagnetic transition, which is given by theta or Tc, which we have called as Tc at times and we have called theta at times. However, if we revisit the same problem from an electronic model, then we get a Stoner criterion, and Stoner criterion tells that the electron-electron interaction multiplied by the density of states at the Fermi level has to exceed 1 for ferromagnetism to occur.